Now let's talk about the final way to do amortized analysis, which is the physicist method. The idea of the physicist method is to define a potential function, which is a function that takes a state of a data structure and maps it to an integer, which is its potential. This is similar in spirit to what you may have learned in high school physics, the idea of potential energy. For instance, if you have a ball and you take it up to the top of a hill, you've increased its potential energy. If you then let the ball roll down the hill, its potential energy decreases and gets converted into kinetic energy, which increases. We do the same sort of thing for our data structure, storing in it the potential to do future work. A couple rules about the potential function. First, phi of h sub 0. So phi is the potential function. H sub 0 is time 0 of the data structure h. So that means the initial state of the data structure. And that has to have a potential of 0. Second rule is that potential is never negative. So at any point in time, phi of h sub t is greater than or equal to 0. All right. So once we've defined a potential function, we can then say what amortized cost is. The amortized cost of an operation t is c sub t, the true cost, plus the change in potential between before doing the operation and after doing the operation. So before doing the operation, we have phi of h sub t minus 1. After, we have phi of h sub t. So it's c sub t plus phi of h sub t minus phi of h sub t minus 1. What we need to do is choose a function phi such that if the actual cost is small, then we want the potential to increase so that we're saving up some potential for doing later work. And if c sub t is large, then we want the potential to decrease in a way to sort of pay for that work. So the cost of n operations is the sum of the true costs, which is the summation from I equals 1 to n of c sub I. And what we want to do is relate the sum of the true costs to the sum of the amortized costs. So the sum of the amortized costs is the summation from I equals 1 to n of the definition of an amortized cost, which is c sub I plus phi of h sub I minus phi of h sub I minus 1. Well, we could just rewrite that. So removing the summation as c sub 1 plus phi of h sub 1 minus phi of h sub 0 plus c sub 2 plus phi of h sub 2 minus phi of h sub 1 and so on. What's important to note is that we have a phi of h sub 1 in the first line and a minus phi of h sub 1 in the second line. So those two cancel out. Similarly, we'll have a phi of h sub 2 in the second line, and we have a phi of h sub 3 when we look at the amortized cost at time 3. And that goes on until at time n minus 1, we would have a phi of h sub n minus 1 positive and a negative phi of h sub n minus 1 negative. So we have all these cancellations, and all we're left with is the very first term, phi of h sub 0, negative phi of h sub 0, and the very last term in the last line, which is phi of h sub n. So this really just equals phi of h sub n minus phi of h sub 0, because all the other phis cancel, plus the summation from I equals 1 to n of c sub I. That is the true cost. Since phi of h sub n is non-negative and phi of h sub 0 is 0, this value is greater than or equal to just the summation of the true costs. What that means then is we've come up with a lower bound on the sum of the amortized costs, which is the sum of the true costs. So therefore, if we want to look at a cost of an entire sequence of operations, we know it's at least the sum of the true costs. So let's look at applying this physicist method to the dynamic array. So we're going to look at n calls to pushback. Phi of h, so at any given time the data structure is going to be 2 times the size minus the capacity. So as the size increases, the potential is going to be increasing for a given fixed capacity. Phi of h sub 0, so we want to make sure that our phi function satisfies our requirements. So first, phi of h sub 0 is 2 times 0 minus 0, assuming we have an initial array of size 0, and that's just 0. Also, phi of h sub I is 2 times size minus capacity. We know the size is at least capacity over 2, so therefore 2 times size minus capacity is greater than 0. Now let's look at our amortized cost. So we're going to assume we don't have to do a resize, and let's look at the amortized cost. So we add a particular element I, and the amortized cost is the cost of insertion plus phi of h sub I minus phi of h sub I minus 1. So the cost of insertion is just going to be 1 because we're adding an element and we don't have to do any moving of elements. Phi of h sub I is 2 times size of I minus the capacity of I, and phi of h sub I minus 1 is 2 times size I minus 1 minus capacity I minus 1. Well, what do we know? Since we're not resizing, the capacities don't change. So the capacities cancel themselves out. And so we are left with 2 times the difference in sizes. But what's the difference in size? The difference in size is just 1 because we added 1 element. So this is just 1 plus 2 times 1, or 3. It's no accident that this 3 is the same value that we saw when we used the Banker's method. And then let's look at the cost when we have to do a resize. So we're going to define here K is size sub I minus 1, which is the same thing as capacity sub I minus 1. Why is it the same? Because we're about to do a resize. So that means that after the previous operation, we must have made the dynamic array full. And then phi of h sub I minus 1 is just 2 times the old size minus the old capacity, and that's just 2 times k minus k, or k. Phi of h sub I is 2 times size sub I minus capacity of I, and that's 2 times k plus 1, because the size sub I is just 1 more than size of I minus 1, minus 2k. Why 2k? Because we double the capacity each time. So that's just equal to 2. So the amortized cost of adding the element is c sub I plus phi of h sub I minus phi of h sub I minus 1, which is just size of I, because that's the number of elements we have to move size of I minus 1 elements and then add the 1 new element. So that's size of I. So we have size of I plus 2 minus k, which is just k plus 1 plus 2 minus k, which is 3. So what we have seen now is that the amortized cost using the physicist method of adding elements is 3.